So before discussing the topic linear algebra, first we shall see what you mean by linear algebra. ಇಲ್ಲಿ linear ಅಂತಕ್ಕಂಥ term that denotes it is connected with a line. If we want to take a point in a xy plane, x1, y1, then from the origin you may draw a line up to the point x1, y1. So that point from the origin 0, 0 to the point x1, y1, it is a line. It is denoted as a vector. It is a vector. If you write it in terms of a vector, you will be writing it as x1, y1. Now suppose you take a point in a space with 3 perpendicular axes x, y, z. Then the point can be represented by x1, y1, z1. And again there is a line or a vector from the point 0, 0 to x1, y1, z1. So such a type a vector is always nothing but a line in a space. You may mean a vector in general denotes a line in space. So linear means it is connected to lines. Algebra means a particular non-empty set having more than one binary operations. It is called as algebra with the specific conditions on the binary operations. So linear algebra means a set of lines or set of vectors having some algebraic properties. So this is all about the linear algebra. First we shall see what is a field f. A field f is as I told earlier, it is a commutative division ring with unity. Or you may say that a ring with unity in which all the non-zero elements form a multiplication group. So it is a commutative division ring with unity, field f. Now let us consider another one non-empty set V. Now we define two binary operations. One is addition, that is from V cross V to V itself, and another one from F cross V to V, that is scalar multiplication we call, or the dot multiplication. So from V cross V to V there is a binary operation what we call addition in V. So if for any two elements in V, alpha plus beta is another element in V, and if we consider a scalar C contained in the field F, the elements of the field F are called as scalars. So if we consider a scalar as an element of F, say C contained in F, and a vector alpha contained in V, C dot alpha is in V. So it is a binary operation from F cross V to V. So with these two binary operation, one is the internal binary operation and another one is the external binary operation what we call scalar multiplication. If with these two binary operations a non-empty set V satisfies what we call vector axioms, then we say that V is a vector space. So what are those vector space axioms? So let us see. For every alpha beta contained in V and for some CD contained in F, the first thing is V must be an abelian group under addition. And that is, when we say that V is an abelian group, it must satisfy the closure law, associative law, the existence of identity with respect to addition, and the last one is inverse for every element of V with respect to addition. So for any alpha contained in V, you may see that alpha plus beta is also contained in V, closure law must be satisfied, and for any three elements in V, alpha, beta, gamma, alpha plus beta plus gamma is equal to alpha plus beta plus gamma. And if you take another element, say null vector or zero vector, or simply we denote it by 0, 0 plus alpha is equal to alpha plus 0, then it is equals to alpha itself. So 0 is the identity element of V. And the next one is inverse. For every alpha content in V, there must exist some minus alpha content in V such that alpha plus minus alpha is equal to 0. And the last one axiom is the addition must be commutative, that is alpha plus beta is equal to beta plus alpha. So the first one is V is an abelian group under addition. That means it must satisfy all these axioms. One is closure law, associative law, existence of identity, existence of inverse for every non-zero element of V, and the addition must be commutative. Then only we can say that V is an abelian group under addition. And after that, there are some laws for the external compositions. The first two are called as distributive laws. One is called as vector multiplication is distributive over scalar addition, that is alpha dot c plus d is equal to alpha dot c plus d dot alpha. And another one is scalar multiplication is distributive over vector addition, that is c dot alpha plus beta is equal to c dot alpha plus c dot beta. So these are the distributive laws. Here you may note that one may say that it is the left distributive law or right distributive according whether the multiplication appears from the left or from the right. We can call them as left distributive law as well as right distributive law. Third one is algebraic law. We say that for every CD contained in F and alpha contained in V, C dot D into alpha is equal to C into D alpha. It is called as algebraic law. And fourth one is 1 dot alpha is equal to alpha dot 1 is the unit element of F. 1 dot alpha is equal to alpha, where 1 is the unit element of the field F. Unit element with respect to multiplication, we may say. So when all these conditions are satisfied, then V is said to be a vector space over the field F. We shall take certain examples. As I told earlier, a line in space with respect to n coordinates can be written as V is equal to x1, x2, x3 and so on xn. Of course, every vector we can say that it is an ordered n tuple of elements of F. A vector can be said that it is an ordered n tuple of elements of F. So usually we write it as VNF. ಇಲ್ಲಿ n subscription ಇದೆ. n subscription ಇದೆ ಅಂತಂದ್ರೆ that means it has n elements as its components. x1, x2, xn are called as components, but these are nothing but the elements of F, and we say that the dimension of VNF is n itself. Of course, we shall discuss about what we mean by dimension and all those things later in the next classes. But here usually there are n components x1, x2, x3, xn, and each xi is an element of F. So we first define the addition in V. Let u and v be two vectors. Then we define u plus v or v plus u as it must be commutative. You can see that one. So commutative, you can see that one. We define u plus v is equal to, we add vectors component wise, that is x1 is added to y1, x2 is added to y2 and so on, and each component is written in terms of u plus v. And you may see that again in addition there will be n components, so it is contained in v and f. And similarly, if you define c dot v is equal to c into x1 comma c into x2 and so on, c into xn, again this vector also has n components, and c1 x1 cx2 and so on are all the elements of F, so it is also again contained in V. So both these operations are well defined, and the codomain is V itself. So we can see that these operations are well defined, and let us see whether these forms a vector space, that is V and F with these binary operations forms a vector space or not. So we try to verify the results. Of course, here you note that C dot U plus V is equal to C dot U plus C dot V. What is more important here, if we want to verify whether V and F is an additive abelian group or not, you simply verify that this rule, that is C dot U plus V is equal to C dot U plus C dot V. If this is satisfied, then definitely it is an additive group. And the other one, commutative law also holds, you may note that one. So I can write V and F plus is a additive abelian group. Now you want to verify the distributive laws. Here we are taking the what we call vector multiplication is distributive or scalar addition. So C plus D into V, we can write it as C plus D into x1 and so on, using the definition of scalar multiplication, that is V is equal to x1 x2 xn. So C plus D dot V is equal to C plus D into x1, C plus D into x2 and so on. And writing separately, we can see that one, it is equals to C dot V plus D dot V. So you may see that vector multiplication is distributive or scalar addition. Hence the distributive law of vector multiplication over scalar addition is holds. Similarly, you can see that the algebraic rules also holds. So all the remaining laws holds. Therefore, you can see that it satisfies the all conditions of vector space.